Okay, thank you very much. My name is Boris, and I'll share the talk with Ludovic. So we are dealing with geodynamic applications on one hand and ice dynamics on the other hand. You may be wondering what the heck is that about and why are they similar? Well, geodynamics on the scale of the plate, on geological timescales, the Earth behaves like a fluid, a complex fluid with very complex behavior that can break, that can float, flow on a viscous manner depending on what the temperature, stresses, etc. are. On the other hand, we have ice sheet dynamics, and the basic equations that govern this are quite similar. And in both cases, we have a very big difference in scales that goes on the scale from the Earth, from thousands of kilometers, to the scale of shear zones that are hundreds of meters that play a crucial role in determining whether we have plate tectonics or not. And the same happens with ice sheet dynamics, where the flow is a very large ice sheet, but much of this deformation is localized in ice streams that are much smaller in scale. So in other words, we need high-performance computing to resolve all of this, and that is the background of the GPU4Geo project we have been having over the last few years, where the idea was to build a unified suite of software tools for both ice sheets and geodynamic applications. And the focus here, as the name says it, is on GPU computing, and Ludovic will later show the results of their allocation, extreme scale allocation on the biggest HPC machine in Europe that is GPU based. So classically, codes in this community have been big monolithic codes with 50,000, 100,000, 100,000 of lines of code. That makes it very intimidating for a new PhD student to start working with these codes or add new features to it. And thanks to the power of Julia, it is possible to make this in a much more modular sense. And we have therefore developed a range of packages that together can have the same functionality, but can also be used individually. And the main advantage that we experience with this is that we have many more contributors to each of the individual packages, because it's easier and less intimidating for newcomers to add to this. So in GPU4Geo, I have a bunch of packages we will discuss later. They are developed on a bunch of tools. Parallel stencil and implicit global grid has already been discussed in the last few JuliaCons, Stellar Räss, Chimney, and then we are basing this on things like CUDA.jl or MPI.jl. The equations we solve in this are the incompressible Stokes equations, or the nearly incompressible Stokes equations, where the challenge is that the material parameters are very strongly varying and nonlinear, and they can vary like 10 orders of magnitude between having melt in one location and having solid rock next to it. They are nonlinear, history dependent. We are using in both applications a staggered grade finite difference formulation, because that is a stable scheme that turns out to be very, very scalable and works well. It's good for high performance. Irregular boundaries require some special care, and that can, for example, be done with an immerse boundary methods. We have the packages we have been developing are based in basically two organizations, Julia Geodynamics and Pseudo-Transient Solvers. And there's lots of people that have contributed to that. Albert Montserrat is one of the main postdocs that has been hired in this project, and he does an incredible work. Same with Ivan, who's here and gave a talk, what was it, yesterday or so. So if you want to have a look, give this a look. So one of the packages, what we are often dealing with when we are trying to model geological systems, is that there is lots of data available, but in all kinds of formats. And creating an initial model setup from all that data is actually not that straightforward. And that is why we have developed something called the geophysical model generator, that basically allows us to import the data, project them from spherical coordinates to Cartesian coordinates, create an initial model setup, run simulations with that, and get the simulation results back and compare it again with the available data. And that is a very simple package, but it's actually still quite quite useful to collect different data sets. And this is an example of the Jura Mountains in Switzerland, where we automatically download the topography of the region. You take a geological map, drape it on top of it. You have a sketch from the geological paper that you can put as a cross section, simply as a screenshot from the sketch, and you have like some digital map of where the basement rocks are. So that is something that we use as an input model generator. The core, or one of the main packages we are dealing with, is called GeoParams. And GeoParams deals with the fact that many geodynamic codes have very complex constitutive relationships. Viscoelastoplastic, they are nonlinear, and much of the complexity of developing a geodynamic code is actually in developing this kind of constitutive relationships. The point is that these relationships, they are always pointwise calculations. So it doesn't matter if you have a finite element code, a finite difference code, a spectral element code, you always need to do this kind of calculations, and they're independent of the discretization. So the idea of the package is therefore to create a database of lab-based parameters. Takes quite a bit of time to collect all of that. It provides a computational engine. It provides plotting routines, unit conversions. It's GPU compatible, and it's differentiable, and it allows you to set up a complicated constitutive relationship like written here, simply on the command line, and then you get a little graph of how this looks like in principle, and you can extend this at free will. And that is quite powerful because we have then one simple callback API that is compute tau second that updates the stress tensor, and if your code uses this, then a new constitutive relationship added to GeoParams will automatically be taken into account. So you add it once, and then you have a whole range of codes that can use this. And this is actually quite powerful. It works on GPUs, and it is also relatively fast. So let's give you a quick example. This is a typical equation of state where density depends on temperature and pressure with a few parameters. So if you would just code this up in Julia, you would call this compute density 0 with a bunch of parameters. And we have also coded this up in GeoParams, which is basically the same. If we compute this and benchmark it, we see we have 1 nanosecond here, and we have the same time there. So we lose no time by using GeoParams. Typically, we have in our simulations not one type of rock, but we have typical many different types of rocks. And we often code them up with different phases. So phase 1 is rock type 1, and phase 2 has slightly different parameters. So let's have a look at how you deal with that. So if we have the handmade kernel, then you can say, okay, we initialize an array of phases, which is the type of rock that you have, and then the naive implementation of that would use if statement, and you loop over each of the phases, and depending on what you do, you use these parameters. And you see in this particular example, this takes 192 nanoseconds with branching. Now you can, of course, say, well, using if statements is bad, so let's get rid of that. You get a faster code. So if we do the same without if statements, it is indeed a little bit faster, 160 nanoseconds. But if we do the same with GeoParams, the same type of loop, we are 4 times faster, and that is because we are using multiple dispatch and a few other tricks in the background. So you see that this actually really brings an advantage of having this in a central package rather than having to code this up yourself in each individual code. You can also compare this with a C++ implementation here, and you see that the case, and this is a 2D case, you see if we use the branching, then we have about the same speed between C++ and Julia, also with the branchless case. And if we use GeoParams, we are still a little bit faster, which is probably that because our C++ implementation is maybe not totally optimized. But in any case, it shows that Julia certainly is compatible with the compiled language, and very useful because it is modular. So just to give you an example of how this works in practice. In practice, in your code, you would specify the different material parameters in your input setup, and then in your actual code, you would run this kind of simulations, and this is now done on a GPU using a so-called pseudo-transient solution method that simulates the breaking of rocks. Another ingredient in many of the geodynamic codes is that we use the particle and cell advection scheme to deal with large deformations and complex geometries. And this has been implemented by Albert in the package Just Pick that works on multi-GPUs and on CPUs. Just Relax is our code that basically combines all of this into a bunch of benchmarked examples that run in 2D and 3D on CPU and GPU, on multi-GPUs. And here are some examples of using Just Relax to simulate the subduction of tectonic plates on a 1,000-kilometer scale in 2D and 3D. This is an example of a PhD student working in mines who is currently trying to simulate massive volcanic eruptions and how they happen on a million-year time scale. And you see the breaking of the rock and a big magma chamber. We can also, so this is on a scale of 20 kilometers. We can also look at this on a much smaller scale. This is the scale of 100 meters, where we simulate what happens if you have magma that is injected into the earth, into rocks that are solid. Turns out the magma cools, it starts to crystallize, the crystals are heavier, it sinks down, it heats up the host rock that starts melting, and these are phenomena that we can simulate in a rather straightforward manner. If we're only interested in looking at the thermal structure of magmatic systems, there is a package called Magma Thermokinematics, which simulates this in 2D or 3D. The advantage is that it is a very short code, so it's very easy to apply to different locations. And again, this works with all the packages I discussed before. So if we add a new type of melt or heating, crystallization, parameterization, we would do that in GeoParams, and then this would then be available in all the codes you just saw before. Yeah, so that makes it very modular. So at this stage, I would like to hand over to Ludovic, who will explain you how they broke the world record of doing the world's largest resolution simulation of a Stokes problem a few weeks ago.
Thank you. Yeah, well, thank you. Hi, everyone. Well, I don't know. It's at least European scale on a kind of custom code. It's like certainly some good numbers. So yeah, in the remaining of the presentation, I'll talk a bit about some of the HPC insights of the project, focusing more on the ice flow part of what we were doing there. So as Boris introduced, like one of the things that is interesting to us is this kind of localization of flows. So kind of why on this, for example, like Antarctica, Greenland, or big or smaller ice sheets, like nothing moves, but unless some very few region where all the action happens, and kind of these streams, as they called. And like here one sees one where like fast flow in the middle, and these stream margins where you have like extreme shear deformation. And this is just to give an idea of like an idealist setup, but basically one has like these corridors of fast flowing ice, and the question is like, well, what leads to what handles the stability? And we're investigating these kind of thermomechanical feedbacks, such that, for example, shear heating, like you have in a region where we concentrate stress and strain, it would heat up, weaken the ice, and like start to get this localization process. But to do this at large scale and in 3D, one needs tools, and tools that be able to leverage GPUs. So I kind of won't make the whole GPU propaganda, but basically, kind of GPUs are currently the way to kind of get extreme scale computation at extreme scale performance. And so we are developing these fast ice solvers, and they are like just given overviews. So well, basically for now we handle full Stokes in isothermal and thermomechanical setting, but ideally we have a list of adds-on. And yeah, so there's some tooling around, so how you pre-process and post-process, like treat this immersed boundary condition. That's pretty challenging because while it needs to be, distributed, and like kind of one cannot lose performance on that. And obviously, like for example, having immersed boundary, it by construction seems to be like, well, I need to do a lot of checks, they're potentially branching, etc. So there, well, we do it with a bit kind of using variation approach, but kind of using masking rather than branching, so just things that don't kill your performance on the GPU especially. And well, we rely on a kind of core package that provides the functionality to handle grid fields and operators that Ivan mostly spent time to discuss earlier this week. But the main idea is really that we need to target GPUs and latest generations. So for example, latest Grace Hopper from NVIDIA, or like what we were now having allocation on, like AMD, these MI250, which are like one of the latest available AMD GPUs. And this is kind of one project that we currently, well, kind of in the final phase, which is called Stream, and where we got one of the few extreme scale allocations, so the largest allocation on a European supercomputer, the largest in Europe, which is Lumi. And yeah, it has about 3,000 nodes, and each of these nodes has 8 of these MI250X GPUs. And so we got awarded 5 million GPU hours to make a, well, kind of different type of simulation, including like large runs. And in this project, we were focusing on first on this on the Vavilov ice cap, because well, we realized that it was like, well, there's some challenges on the way. So this has like some regarding like geometry and aspect ratio and boundary condition. This was like a first thing to start with, and so we're towards like doing different kind of runs there. And so one sees like the color scale is like the magnitude of ice flow, and the red part is the region that we see on satellite images where there's these streams that localizes, and such kind of simulation, they're like really well, extremely expensive. So well, that kind of wouldn't be possible if you don't run on many nodes. And so regarding the performance, so well, a part of doing some simulation, we were also doing benchmarking, testing, fixing a lot of things. But yeah, like recently we finally kind of have an implementation that's more or less stable, and we converged to something like that was kind of trying to, well, get everything the right way, such that so what you see here is like a weak scaling. So we run a kind of a 640 cubes on one GPU. That's the local problem size, and then we increase the problem size together, like linearly together with the number of GPUs, such that using more GPUs, they all run the same local problem size. And so we went from 1 GPU to 21,952 GPUs, and timing the same amount of work, local work, we basically lose only 3% of kind of time from going from 1 to basically the full machine. And this is like running Julia that was, well, on the machine that was downloaded with Julia up, and MPI preferences that was, well, just using MPI preference to set up where to find the MPI library. So it was like a 2-click setup. And well, it's pretty cool that kind of, well, running, just installing Julia up on the supercomputer, hitting once the MPI preferences, and having, well, spent some time on making the implementation behind good, it kind of just works. And yeah, so we're pretty excited about that. And so the whole thing here, and quite some work went into this overlapping communication with computation, because at large scale it's where you would lose time. So while increasing the number of GPUs involved would increase communication between them, between processes. It's all point to point, but still overall it kind of increases some entropy in the machine, and then you could easily, well, without this it would just go down to a bunch of under 10% fairly quickly. And yeah, and again, Ivan gave some nice insight in his talk that is available online. So how we achieved this, especially, so here we implemented, everything is task-based, like Julia idiomatic, and so we had some things we needed to overcome, some little things. So well, we figured out that these tasks that could be fairly expensive when they hit the finalizers if we spend a lot of tasks, and then we kind of had workarounds and they seem to work. Another thing that we started to look at, but that will be further pushed in the hopefully granted follow-up project, is differentiable modeling. So, well, now we have these distributed GPU codes that can solve Stokes-like problem, and now we're looking into ways to make differentiable modeling. They can leverage differentiable modeling, and the solution scheme we're using, these iterative solvers, we kind of found or revamped a way to be able to use them to solve the adjoint problem. And then if you have a way to efficiently solve forward problem, to efficiently solve an adjoint problem, you can start to do inversions at large scale, which is also a topic that's at least what I find super interesting. And there we combine it with enzyme, and basically that's what I'm showing here. So if we have a forward problem on the top, the way one can phrase the adjoint problem in our case would require to compute this transposed Jacobian, and this we can get in a black box way on the GPU in a distributed fashion from enzyme, which is fairly cool. But there's I guess maybe later or next year there would be if that works out, and we have the project, there could be a talk on that. But now we have a sandbox. We're looking at the glacier in Switzerland, the Aletsch Glacier, for those who recognize. And so, here it works. So we were inverting or trying to retrieve the sliding coefficient, so how much ice deforms versus it slides on the bedrock to fit the observation. So the observation is the truth. In the middle is the velocity one would get if one doesn't have any sliding, so only ice deformation with a simplified model. And then the third pane is the velocity when you have this sliding at the base that we retrieve this automated work. I'll skip that one, but maybe just to finish also that in general, as Boris said, there is maybe this shift in community. So we tried in geodynamics or Earth computation, Earth science, in geodynamic and ice dynamic as abroad. So slowly, people, more and more people use Julia and Julia at scale. We're teaching a course at ETH that uses Julia, GPUs, and all these same things, and have some activities around it, and that's really, there's some nice momentum around. So to have some time for question and discussion, I leave you with the summary and the conclusion here. And I thank you for your attention.
Yeah, thank you very much. And in the interest of time, the next speaker can already set up everything. And while he's doing that, maybe we have time for one quick question. That's the first one I see.
So I was wondering, the solution methods that you use, are they all explicit or implicit, or is there a mix? And if you need to solve linear systems, are there already good solutions that work massively parallel on GPUs?
To get the extreme scalability, you have to use explicit solution methods. It doesn't work otherwise. The general framework, for example, for using geoparams, also works with implicit codes and with automatic differentiation. So in principle, you can also write an implicit code using the whole framework, but I don't think it will scale to the same to the same size of machines. Yeah. But the advantage is we can reduce duplication of work a lot with this.
Maybe I can just add a little comment. So the iterative scheme, it uses kind of what we're using here is So both cases so we use kind of iterative solvers, but so the solution is implicit, but the iteration strategy is an explicit one. But so that's kind of, it's still implicit solution, so it's not explicit. It's kind of, it solves elliptic equations, so we have a implicit solve.
Great. Thank you very much again.